most disturbing truth about your existence. You are surrounded by a force so powerful, so utterly alien, that it is actively tearing the fabric of reality apart, and it makes up nearly 70% of everything that is. Stop for a moment and look up at the night sky. Everything you see, every star, every galaxy, every swirling nebula, all of the bright, familiar matter that makes up your body, the Earth, and the entire observable cosmos is just a cosmic afterthought. It is a mere 5% of the total inventory. The rest is an invisible, unknown, and relentless entity we call dark energy. It is not a gentle push. It is an accelerating, exponential shove, scaling up the distance between galaxies, between star clusters, and, potentially, between the very atoms that hold you together. This is the ultimate cosmic horror. A fundamental force we cannot see, cannot touch, and cannot explain, and yet it dictates the ultimate fate of the universe. I know what you are thinking. How can something so dominant, so all-encompassing, remain a total mystery to the most brilliant minds on our planet? How can the fundamental structure of reality be governed by a number that our most refined theories predict should be so massive that it would have torn the universe apart billions of years ago, but which, instead, appears to be almost zero? This is not a story about a scientific gap. It is a story about a chasm, a profound contradiction at the heart of physics that threatens to unravel everything we thought we knew about space, time, and the vacuum itself. Imagine yourself standing in the early universe, just a few billion years after the Big Bang. The universe is a chaotic, dense, and exhilarating place. Everything is flying apart, yes, but the overwhelming force of gravity, the collective pull of all the matter and dark matter, is working to slow that expansion down. The cosmos is decelerating, like a ball thrown straight up into the air, fighting against the Earth's gravity. Every scientist for decades knew this was the script. It was a matter of simple physics. Matter pulls, and gravity wins, or at least slows the showdown. The only question was whether gravity was strong enough to eventually halt the expansion and cause the universe to collapse back in a big crunch, or if it would merely coast forever, gradually cooling into a big freeze. The mission was simple. Measure the deceleration. How fast is the universe slowing down? To answer this, astronomers needed a cosmic yardstick, a way to measure truly enormous cosmological distances with precision. And that brings us to one of the most elegant and explosive tools in the astrophysicist's toolkit: the Type 1, a supernova. You might be wondering, what makes these particular stellar explosions so special? They are what we call standard candles. Think of a standard candle as a light bulb with a known fixed wattage. If you know exactly how bright a light bulb is supposed to be, you can determine how far away it is simply by how dim it appears. A dimmer light means a greater distance. Type 1. A supernovae are the perfect cosmic standard candle. They occur when a white dwarf star, the dense, burnt-out core of a star like our Sun, siphons matter from a binary companion. As the white dwarf accumulates mass, it approaches a critical limit, known as the Chandrasekhar limit, which is about 1.4 times the mass of our Sun. When it hits that exact mass, the pressure and temperature ignite runaway nuclear fusion in a catastrophic explosion. Because this trigger mechanism is always the same, the star always explodes at the same mass. The intrinsic, absolute brightness of every single Type 1A supernova is virtually identical. In the late 1990s, two independent teams of astronomers set out to measure these explosions in distant galaxies. The Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, co-led by Brian Schmidt and Adam Rees, were looking for evidence of the expected cosmic slowdown. They looked farther out into space, which, because light takes time to travel, meant they were looking back in time, observing supernova that exploded billions of years ago. They carefully measured the apparent brightness of these distant cosmic explosions. And the results? They were not just wrong. They were cosmically, fundamentally, mind-bendingly wrong. The distant supernova were dimmer than they should have been, significantly dimmer. I know what you are thinking. Dimmer means farther away, right? Yes. But this is the crucial part. If the universe had been slowing down, as expected, those ancient, distant galaxies should have been closer to us now than they would be in a constantly expanding universe, meaning the supernovae should have appeared brighter. Instead, the data showed the exact opposite. The galaxies were much farther away than any model of a decelerating universe could account for. The only logical conclusion was that the expansion of the universe was not slowing down. It was accelerating. It was speeding up. In a stunning joint revelation in 1998, these two teams announced their discovery. It was an instant revolution in cosmology, a finding so unexpected that it earned Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. But the discovery only created a deeper, more profound mystery. Something was pushing. Something was counteracting the combined gravitational pull of every galaxy in the cosmos and winning. That something, that repulsive, invisible force that makes up the majority of existence, was named dark energy. So, what exactly is this dark energy? What is the physics behind the cosmic push? The search for an explanation immediately led scientists back to a concept first introduced and later famously retracted by Albert Einstein: the cosmological constant, or lambda. When Einstein first published his theory of general relativity in 1915, he found that his equations predicted a dynamic, unstable universe, one that should either be expanding or contracting. This was before Edwin Hubble observed the expansion of the universe, and at the time, the prevailing scientific view was that the universe was static, unchanging. To make his equations fit the prevailing but incorrect view of a static universe, Einstein added an extra term, a fudge factor, to his equations. He called it lambda, the cosmological constant. This term represented a constant energy density permeating all of space, acting as a repulsive force to perfectly counteract gravity's pull. When Hubble proved the universe was, in fact, expanding, Einstein famously called the introduction of the cosmological constant his biggest blunder. But the supernova data of 1998 showed that the expansion was accelerating, meaning a repulsive force was indeed at work. Einstein's biggest blunder was spectacularly resurrected as the leading candidate for dark energy. The cosmological constant in modern physics is often interpreted as the energy density of the vacuum of space itself. You might assume that empty space is, well, empty. But quantum mechanics tells a far more bizarre story. The vacuum is not inert. It is a roiling, chaotic sea of virtual particles constantly popping into and out of existence, a phenomenon known as quantum foam. This activity gives the vacuum an intrinsic, non-zero energy. If dark energy is indeed this vacuum energy, it has two crucial properties that perfectly explain the observed acceleration. First, its energy density remains constant. Unlike matter and radiation, which become diluted as the universe expands, the energy of the vacuum is an intrinsic property of space itself. As new space is created, new vacuum energy is created with it, keeping the density fixed. Second, because of the laws of general relativity, this constant energy density exerts a negative pressure. And negative pressure, in the context of general relativity, acts as a gravitational repulsion. It pushes space apart. This seems like a tidy solution, right? Dark energy is simply the energy of the quantum vacuum. Case closed. But this is where the investigation hits a wall so massive, so incomprehensible, that it has earned the name, the vacuum catastrophe. When physicists use the most fundamental principles of quantum field theory to calculate the expected energy density of the vacuum, the theoretical value of the cosmological constant, they arrive at an enormous number, a truly, unimaginably vast number. And when they compare this theoretical number to the actual observed value of dark energy derived from the supernova data, the numbers do not match. They are off by a staggering factor. How big is the mismatch? 1 followed by 120 zeros. Let that sink in. 1 followed by 120 zeros. This is not a small rounding error. It is the largest discrepancy between theory and observation in the entire history of science. Our best theory of the very small, quantum mechanics, predicts a vacuum energy density that is 120 orders of magnitude larger than the observed vacuum energy density that is shaping the entire cosmos. If the quantum mechanical prediction were correct, that energy density would have been so ridiculously high that the universe would have expanded and torn itself apart almost instantaneously after the Big Bang. No stars, no galaxies, no planets, and certainly no you. The fact that the observed value is nearly zero, but not perfectly zero, it is a tiny, finely tuned number, is the profound, disturbing truth. It suggests that somehow, some unknown mechanism of nature is canceling out most of the vacuum energy, but leaving a tiny, residual amount to drive the cosmic acceleration. This is why many scientists believe the cosmological constant, as simple vacuum energy, cannot be the whole story. The fine-tuning required is too miraculous, too coincidental. This brings us to the second leading candidate, quintessence. If the cosmological constant is static, a fixed property of the vacuum, quintessence is dynamic. Quintessence is a hypothetical form of energy, a type of dynamic scalar field that permeates space. Unlike the cosmological constant, the energy density of this field is not constant. It changes over time and space. Think of it as a field, like the Higgs field, but one that is slowly evolving. As the universe expands, this field rolls down a potential energy landscape, and its energy density changes. Why is this appealing? Because a dynamic field could potentially explain why dark energy only became dominant relatively recently in cosmic history, about 9 billion years after the Big Bang, and it might offer a natural explanation for the current low energy value, bypassing the catastrophic fine-tuning problem. The key to distinguishing between the two lies in a single, crucial number, the equation of state parameter, symbolized by the letter W, which relates the pressure of dark energy to its energy density. For the cosmological constant, W is precisely -1. If W is -1, the dark energy is constant forever. For quintessence, W would be a number slightly greater than -1, meaning its influence changes over time. But there is a third, truly terrifying possibility, one that goes beyond quintessence: the existence of phantom energy, where W is less than -1. This is the ultimate counterintuitive turn. You have to confront the most counterintuitive idea in all of cosmology. We live in a gravity-dominated world. If you drop a pen, gravity pulls it down. If you throw a ball, gravity slows it down. The entire intuitive framework of your life is based on attractive forces. Dark energy is the complete opposite. It is a repulsive, negative pressure that acts like anti-gravity. It is the force that is winning the cosmic tug-of-war. For the first 9 billion years of the universe's history, gravity was the heavyweight champion. Matter, both ordinary and dark, was packed relatively closely together, and its density was high. Gravity's attractive pull was strong enough to ensure that the expansion of the universe was decelerating. But remember, the density of matter drops as the universe expands. As the volume of space increases, the matter is diluted. Dark energy, if it is the cosmological constant, has a constant density. It does not dilute. This is the turning point. As the universe expanded, the density of matter eventually fell below the constant density of dark energy. Around 4 to 5 billion years ago, dark energy became the dominant component of the universe's energy density. It took over the cosmic evolution. Imagine a car that has been slowing down for miles, and suddenly an invisible, constant force engine kicks in and starts pushing the accelerator harder and harder. That is the universe right now. This is the ultimate counterintuitive turn. The universe is not a car coasting to a stop. It is a spacecraft with its thrusters firing continuously, accelerating away from everything. The galaxies we see are not just moving away from us. The space between us and them is stretching faster and faster. But the real shock comes when we consider the future and the possibility of phantom energy, where the equation of state parameter, W, is less than -1. If dark energy is the stable cosmological constant, the future is the big freeze, or heat death. The expansion will continue. Galaxies will race away from each other so fast that their light will be stretched out of the visible spectrum. Eventually, the night sky will go dark. Stars will burn out, black holes will evaporate, and the universe will become a cold, empty, and uniform soup of fundamental particles. A lonely, infinite expanse of nothingness. But if dark energy is phantom energy, the end is far more dramatic. The Big Rip. Phantom energy would mean that the energy density of dark energy is not constant. It actually increases as the universe expands. It gets stronger over time. Think about that for a moment. The more space expands, the more powerful the force pushing the expansion becomes. It is a runaway feedback loop of cosmic destruction. In the Big Rip scenario, the acceleration becomes so violent, so rapid, that it overcomes every binding force in the cosmos, working its way down the scale of existence. First, the force would tear apart the distant clusters of galaxies. Then, it would overcome the gravity holding individual galaxies together, scattering the stars like dust. Next, it would overwhelm the gravitational pull of stars on their planets. And finally, in the very last moments, the repulsive push would overcome the electromagnetic and nuclear forces that hold matter together. It would tear apart molecules, then atoms, and finally even the atomic nuclei themselves. You, your planet, your molecules, and your subatomic particles would be ripped into an infinite singularity of disconnected fundamental debris. This is the terrifying physical consequence of a W value slightly less than -1. We do not know which fate awaits us. The ongoing measurements of W are incredibly difficult, and for now, the data is consistent with W being exactly -1, the stable but still mysterious cosmological constant. But the margin of error is still large enough to leave the door open to the Big Rip. We have traveled from a mysterious cosmic acceleration to the edge of the Big Rip, but we still have not fully addressed the ultimate enigma: the dark universe itself. Dark energy, the accelerating repulsive force, makes up about 68% of the universe's total energy budget. But we have to remember the other major unknown component: dark matter. This makes up about 27%. Look closer at this composition. Ordinary matter, the stuff of stars, gas, dust, and you, is a mere 5%. This means that about 95% of the cosmos is made of things we cannot see, cannot directly detect, and cannot explain with the standard model of particle physics. Dark matter is the cosmic glue. It exerts a gravitational pull, holding galaxies and clusters of galaxies together. We know it is there because we can measure its gravitational effects on the visible matter. It is the missing mass required to make galaxies spin as fast as they do without flying apart. Dark energy is the cosmic anti-glue. It exerts a repulsive push, driving the accelerating expansion of space itself. You might be wondering, are dark matter and dark energy related? Are they two sides of the same invisible coin? Currently, the two are treated as completely separate phenomena. Dark matter clusters. Dark energy is uniform. Dark matter attracts. Dark energy repels. But the fact that they are both dark, both outside the realm of known physics, suggests a deeper, unified theory might be missing. The search for that unified theory, for the true nature of dark energy, is the most active and challenging area in modern cosmology. Large-scale experiments are currently underway, dedicated to precisely mapping the expansion history of the universe. Projects like the Dark Energy Survey, or DES, and future missions like the European Space Agency's Euclid Telescope and NASA's Roman Space Telescope are meticulously charting the positions and distances of millions of galaxies and supernovae. Their goal is to measure that crucial equation of state parameter, W, with enough precision to finally distinguish between the cosmological constant, quintessence, and the terrifying phantom energy. They are looking for the subtle signature of how dark energy has changed over cosmic time, or if it has changed at all. If W is not precisely -1, then the universe is governed by a dynamic field, and the path to a new fundamental physics is clear. If W is perfectly -1, the mystery only deepens. It means Einstein's cosmological constant is correct, but we are still left with the vacuum catastrophe, the 120 orders of magnitude discrepancy. This would force us to fundamentally rethink our understanding of quantum gravity and the nature of the vacuum. In essence, dark energy is not just a placeholder for a missing explanation, it is a mirror reflecting the fundamental incompleteness of our physics. The existence of this dominant, repulsive force implies that our best theories, general relativity and quantum mechanics, are fundamentally incompatible or incomplete when describing the universe at its largest scales. It forces us to ask the ultimate metacognitive question: is the universe fundamentally understandable by the human mind? Look closer at this paradox. The fact that dark energy exists at all is what allowed the universe to become large enough, complex enough, and old enough for you to be here, asking these questions. If the energy was 120 orders of magnitude higher, it would have ripped us apart. If it was 0, the universe might have collapsed in a big crunch. The current density of dark energy is a cosmic sweet spot, a finely tuned number that allows for the formation of stars, galaxies, and life. Whether it is the constant, finely tuned energy of the vacuum, a dynamic, evolving field of quintessence, or the runaway engine of phantom energy that promises a big rip, the truth remains the same. The universe is not what it seems. The vast majority of reality is dark, unknown, and governed by a force that pushes rather than pulls. And the search for its true identity is the search for the final, missing chapter in the story of the cosmos. It is the ultimate investigation into the unsettling truth that we are merely 5% players in a 95% mystery. And the clock is ticking on the universe's accelerating, inevitable future.